This example requires us to find the Fourier transform of a Gaussian function. The Gaussian function is defined just here, and we're also given this useful integral, which we'll see we need to use later on. We're also given in the red box the definition of the Fourier transform. In this example, the original function is a function of x, and so the Fourier transform will be a function of f of k. So we can write down the Fourier transform. F of k is equal to 1 divided by the square root of 2 pi, and then we have the integral. Now the Gaussian function extends between minus and plus infinity, so the limits on our integral are plus and minus infinity. And then we have the function f of x, that's equal to, there's a prefactor a divided by 2 pi, and that's all in the square root sign, and then e to the minus a x squared over 2, and then we have to multiply by the complex exponential e to the minus kx dx, like that. We can now write this as 1 divided by the square root of 2 pi. We can take the prefactor of f of x outside the integral, that's just a constant, a divided by 2 pi, again all in the square root, and then the integral between minus infinity plus infinity. The integrand is just the product of two exponentials, so we can write that as a single exponential where the argument of this exponential is just the sum of the original two exponentials. So we get this result here. Now in the question we're also given the useful integral, that the integral between minus infinity plus infinity e to the minus n x squared minus jx dx, that's equal to the square root of pi divided by n e to the j squared over 4n, where n and j are constants. It's important to note that the j here is not the square root of minus 1, it's just any arbitrary constant. So what we need to do now is compare these two integrals. We can see that both of them involve an exponential with an x squared term and an x term. So we need to compare the coefficients. So if we look at the Fourier transform, the coefficient of x squared is a over 2, and the equation in blue, the coefficient of x squared is just n. So we have that n is equal to a over 2, and then if we compare the coefficients of the linear term, we can see in the Fourier transform the coefficient is ik, and in the blue equation this is just equal to j. So we can now evaluate our Fourier transform by using the appropriate values of n and j. So we can write that f of k is equal to 1 divided by the square root of 2 pi, and then it's the square root of a divided by 2 pi, and then we're going to get a factor of the square root of pi divided by n, so that's pi, and then n is equal to a divided by 2, and then we get the exponential e to the j squared divided by 4n. J squared is I times k squared, and then we divide through by 4n, so that's 4 times a divided by 2. So that's now calculated the Fourier transform. We can do quite a bit of simplification. If we look at this, we've got 2 factors of the square root of 2 pi, so we can write 1 divided by just 2 pi. We've also got a factor of a there, the square root of a, we've got a square root of a there, so we can write those square roots of a's just cancel out, and then in the final term before the exponential we've got pi divided by a half, so that just gives me the square root of 2 pi, like that. If we now look at the exponential, we can see that on the top of the argument of the exponential we've got a term ik squared. I is equal to the square root of minus 1, so I squared is just minus 1, so we get e to the minus k squared, and then in the denominator we've got 4a divided by 2, that just gives me divided by 2a. And then the final thing we can notice is that the prefactor now we've got a square root of 2 pi and we've got 1 over 2 pi. So we can write this as 1 divided by the square root 2 pi e to the minus k squared divided by 2a, like that. And that gives us the Fourier transform of our original function. What we can see is that the Fourier transform is now also a Gaussian function. It's a function of k, but it's still a Gaussian function. So we've shown that the Fourier transform of a Gaussian function itself is also a Gaussian function. Now, although the question doesn't ask us to do so, it's interesting to look at the widths of the original function and also the width of the Fourier transform. We saw that the original function f of x was proportional to e to the minus ax squared over 2. This is a Gaussian function, so it has a maximum when x is equal to 0, and as x increases, it falls off rapidly and approaches 0 as x tends to infinity. We can define the width by looking at where the function falls to 1 divided by e of its original value, and that occurs when ax squared over 2 is equal to 1, because in this case we'll just get e to the minus 1. So from this we can write that x squared is equal to 2 over a, or x is equal to plus or minus the square root of 2 over a. What we would now argue is that the width of the function can be taken between these 2 points. So delta x is equal to 2 the square root of 2 divided by a. We can do exactly the same for f of k. f of k is proportional to e to the minus k squared over 2a. Again, this will fall off to 1 over e of its original maximum value when k equals 0, when k squared over 2a is equal to 1. So that gives us k squared is equal to 2a, k is equal to plus or minus the square root of 2a, and so we can say that delta k is equal to 2 the square root of 2 times a. And if we compare now the widths of delta x and the width delta k, so the widths of the original function and the widths of the Fourier transform, we can see that delta x is proportional to 1 over the square root of a, and delta k is proportional to the square root of a. So the two widths are inversely proportional to each other. The other way of writing that is to write the product, delta x, delta k, that's equal to 2 square root of 2 over a times 2 the square root of 2a, like that. And that just gives you 2 times 2, and then there's 2 factors of the square root of 2 times 2 again, and we get 8. So we just get a constant. Now the value of the constant is somewhat arbitrary. It depends on how we define the widths of the original functions. We could have defined them when they drop to perhaps a factor of a half of their original value. But overall we'd still get the same result. We find that the widths are inversely proportional to each other. And we've seen that this is a general result of a Fourier transform.